Hello class, this is CSE-5250, section 2 and 60, week 3, spring 2025. So, this video is going to be, well, really I'm just going to cover the first half of the set of slides, so this might take 3 class sessions to get through, because the first thing I want you to do is a Hello World program in Pthreads. So, this is hopefully going to be a quick assignment where we just write a basic Hello World program and just figure out how Pthreads works from there. Alright, so we're going to begin with a reminder of what even is a thread. So some of this is going to be a review from operating systems. If you've taken operating systems in the past, that is CSE-4600, then, well, you probably have to know what this was, because it's one of the main core concepts of operating systems after all. So a process is an instance of a running program. A program by itself on a computer, that's just a file, and by itself it doesn't do anything. It doesn't do anything until we load that program into memory and have the CPU start executing instructions from that program. So those instructions, that's the executable code. That's one part of several parts that go into what a process is. So there's going to be several things loaded into memory, among which is, as I said, the executable code. That's the code that the CPU is running. It's executing lines of code. There's also a block of memory for the stack. The stack is mainly used for like function calls. There's also the heap. That is used for dynamically allocated memory. One key thing about the stack and the heap that you might have learned in operating systems is one grows up, the other grows down, and they grow towards one another, and bad things can happen if they collide. There's also descriptors for what resources are allocated to a process, such as what files does this process have opened. There's also security information and information regarding the state of the program, such as, is this program ready to run? Is this program waiting for resources? Like, is it, for example, waiting for the printer to free up? On most systems, by default, a process's memory is private. No process can access another process's memory. And that's a key thing that the operating system must also uphold. The memory space of one process must not be like messed with by another process. Processes should not interfere with the other processes, and especially the processes should not interfere with the operating system itself. Sometimes we need processes to communicate with one another for tasks where we need multiple processes involved. In such cases, we can set up a shared memory setup. So one other concept in operating systems is the idea of pages. Memory is broken up into pages, and one page in one process's memory space could be loaded in some frame in memory. Here's the thing though. We can set it up so one page is shared between two processes, and that's how we can get processes to share memory. But we want to do more than just share memory. We want to share resources. We want to share executable code. We want to be able to have two processes share basically everything that would be available in a process. Memory, code, resources, everything. How do we do that? Well, at this point it wouldn't really be called a process anymore, but let's just roll with it and say, how do we get this process to work? How can we get processes to work if everything is shared between multiple processes? Let's call it a lightweight processes for now. So, we have these lightweight processes, and we call them lightweight processes because by itself, it's sharing resources from some process. Some other process is sharing its resources with other processes. When this program starts up, it's loaded by the system as a process, And then this process creates multiple lightweight processes. So one process creates multiple processes, but these processes are lightweight because they don't have their own anything. Rather, they're sharing it with the main process. We call this lightweight process typically by another name, a thread. So now we're talking about a multi-threaded program. One process, when it starts, it's just a single so-called thread of execution. That is a sequence of steps to do something. Say, read a file and load its contents into memory. It could be the case that we need to do different processing steps on whatever was in that file. So we say want to calculate the mean, and then we want to calculate the standard deviation, even though the mean is used to calculate the standard deviation. Maybe we want to calculate some other things about it. My point is, instead of loading separate programs, you can just load one program and have each thread do something else with the same data set. So this is the resource sharing I'm talking about. We are making a multi-threaded program here. So we're going to begin by, well, doing exactly that. So this is a Hello World program. You're going to be writing this up. It's a 48-line program. But yeah, let's just head right into it and start actually coding the thing. So I have my other VM is giving problems right now, so I'm using my old one. As I said, the use of a virtual machine is really just an alternative to having to go to the Jack Brown Hall labs and doing the lab there. This is just an alternative way of doing the labs that might be more convenient to you depending on your schedule. So I'll just create a new folder in which I can store all my There we go. I'll create a new folder here. So let's make a brand new program, and it's going to be a Hello World program. I'm not as familiar with the text editors, so the one weird thing that I like to do with creating a new program is typing in vi. Let's go to hello.c. Press escape, press :WQ. That will save the new text file. And then I can just open that with another text editor. So it's a bit of a roundabout process, but I kind of like using the terminal to create files, but at the same time I am so used to using a text editor like this. So this is just Ubuntu's regular old text editor that I'm using. Let's write this program one line at a time. So we need to include standard.io.h. Oh, by the way, this must be done on a Unix system. So it could be a Linux system like Ubuntu, or it could be a Mac, as long as you're able to access the Pthreads library. Which, oh, by the way, that Pthread library is called Pthread.h. Okay, so we're not done with the boilerplate code just yet. We need a global variable. That's going to be a thread count, and then we need a function prototype. And you'll see what this function is for later on. And now we can get to writing the main function. And I'll just write down return null at the end. So if you're not familiar with this main function is being set up. We're setting up this main function so it can accept command line arguments, because this is gonna run as a multi-threaded program, but we don't know how many threads we're gonna be running this program with ahead of time. So we're just gonna pass it in as a command line argument. We need a means of parsing that. So before we get to that, let me just write a few more lines of code. So, pthread t, that is a data type for what is called a thread handle. But notice the star, that's a pointer. We are dynamically allocating an array of thread handles because, again, we don't know how many threads we're going to be running this program with ahead of time. So we're just going to allocate memory as needed to store all of our thread handles. Let's just say it's 10 threads, but it could be as many as 100 or as few as 5. Because we're getting the number of threads as a command line argument, we need to parse the command line arguments. When you type in a command that runs a program, say /program name, parameter 1, parameter 2, and so on, all of that is stored in a character array, argv, that's what it's called. It's an array. argv0 is the name of the program, and argv1 is the very first argument after that. argv2 is the next argument after that. argv3 is the next argument after that, and so on and so forth. We are just gonna pass in one command line argument, and that's gonna be our thread count. So we expect that to be argv1. So let's type that in. So we're gonna say thread count equals strtoll. So strtoll is a function that parses, in this case we're parsing a command line argument into a integer value. The first argument is going to be the text to parse into a string. The second argument, you can just leave that as null. The third argument, we'll just leave that as 10. It can parse anything, it can parse an integer value, well, it can parse text representing a numeric value into one of several bases, or just gonna do base 10. So, as I said, argv1 null 10. And then we're gonna allocate memory for our thread handles. So maybe it would be helpful to maximize this whole thing so it's really in good view. So we're gonna allocate memory for our thread handles. So we're gonna use the malloc function for that. Memory allocate. We're gonna allocate a quantity of memory that is thread count times however big pthread t is. So that is size of pthread t. There we go. Next, we're gonna create threads one by one in a for loop. So to create a thread, we're going to use a function called pthread create. Oh, but first I have to write that for loop. So, oh, by the way, this thread here, that we're just declaring this thread value here ahead of time. So thread equals 0. Thread is less than thread count. Thread plus plus. And in here we're just gonna call pthread create. So there are several things we have to pass into pthread create. I'll get into more detail about what those things are, but for now, I'm just gonna pass in one of our thread handles. Pass in, it's the address of a thread handle, so ampersand thread handles, and then in angle brackets thread. So if this is the first for loop iteration for which thread equals 0, it's gonna be thread handles and then square brackets 0. I'm gonna pass in null here. I'm gonna pass in hello, and if you're paying attention, this hello is this hello. So we're passing in a function in here. And I'm gonna pass in void star thread. I'll explain what this means. I'll explain what this is in a little bit too. For now, let's just keep writing code, and we're gonna have the main thread say hello. So pretty simple. And now we're gonna call something called pthread join. So again, I'll talk about this in detail in a little bit, but basically when we create a thread, the main thread, or I should say the calling thread, typically waits for that created thread to finish its job. We do that by saying pthread join. So since we have a quantity of threads that we don't know ahead of time, we're just going to use another for loop. So for thread equals 0, thread is less than thread count, thread plus plus, and then I'll just say pthread join, and I'll talk about what these arguments are in a little bit as well. But we need to pass in a thread handle, but not the address of a thread handle. So I'll just copy that without the ampersand, and then we'll pass in null. Once that's done, because we had to deal with allocated memory, we need to deallocate that memory when we're done. So that is free thread handles. And my mistake, that should not be a null, that should be a 0 instead. There we go, fixed it up. Now we have a function prototype here, but we haven't written what that function is going to do. So I guess this is a implementation of the thread function that we have up there. So I'm just going to copy this without the semicolon and start writing away. So the rank here is being passed in as data type of void star, but we need to cast that to a long. A long is just a, for our purposes, we're just gonna pretend it's a 64-bit integer. That's not always the case, but let's just pretend that it is. Here we're gonna print f from hello world percent ld of percent d exclamation point \n, and then my rank, and then thread count. There we go. And then return null. There we go. So that is our entire hello world program fully written out. Let's open up this terminal again, and I need to type in a command to compile it. So that would be it's a bit more involved than your typical compile command, because there are a few more things you have to include. That is going to be gcc-g-o, the name of the file, well, any file extensions. In this case, it's just hello. And then the file name, that is going to be the source code file, hello.c, and then -lp thread. Not every system may require that LP thread over there. And by the way, it's LP thread singular, not LP threads plural. Also, one thing I forgot to include is something else called dash wall. So what this is gonna do, it's short for warn all. It basically prints out warning messages that are there to help you write cleaner code. It's optional, but it is a good idea to have. So let's press enter, and hopefully it compiles. Okay, now it's just compiled. Now I can just simply do /hello and press enter, right? No, we got a seg fault, and that's simply because this is a program that is expecting us to type in some number representing the number of threads we want our program to run with. So let's try that again, but I'm gonna add in a space and then 10. There we go. Hello world from thread 0 of 10, 1 of 10, 2 of 10, 3, 5, 4, 7, 6. Hey, wait a minute. It's not in the right order, and that's okay. This is kind of to be expected. And that's because when we create all these threads, the CPU scheduler is likely going to have to make a decision of, okay, should I run this? Okay, so the main thread just forked into a bunch of threads. Do I keep running the main thread, or do I run one of these newly created threads? So that's part of the reason why it might show up out of order. Also, this virtual machine that I have running here, it is only running with 4 processors, and there are 10 plus the main thread. There are 11 threads that need to be run. So I can only run up to 4 threads at a time because I am limited to how much system resources I can give to this virtual machine right now. My point is, those could be the fact that there are more threads than there are processors, and the fact that the CPU schedule might make varying decisions on which thread to run next might influence the order in which these threads print out hello world. Okay, so we have our program done. So I'm just gonna have this be a quick assignment for you to do. It's a simple hello world program. Just write hello world and then run it maybe 1 or 2 times. So you might see instructions on what your first assignment will call for. Let's talk about what's going on. What is making this program tick? So of course we need the Pthreads library, that is pthread.h. We have our global variable that is being used to store the thread count that we eventually parse using strtool. As I said, we have the main function set up so it can accept command line arguments. So int argc character star argv curly square brackets. As I said, we use strtool to get the number of threads from the command line. strtool converts a string into a long integer, so it accepts 3 arguments. So constant character start number p, that is a string that is to be parsed as a number, and p, don't worry about that, we'll just pass a null for that. That is the second argument. The third argument is the base. As I said, we're going to be working with the base 10 here, so just pass in 10. The number 10, 1, 0. Next, we need a thread handle. So pthread t star, that is a pointer to thread handles. Pthread t is a data type for a data structure used to store thread information. It's called a thread handle, and every thread has a thread handle. We are using dynamically allocated memory for this because, once again, we don't know how many threads we're going to be running our program with, so let's just allocate as much memory as needed. Pthread create. We call that to create a thread. When we're doing this in a for loop, of course, but let's get to the meat and potatoes of what pthread create does. Okay, pthread creates a new thread. It requires 4 arguments. The first argument is a pointer to a thread handle. Before we do that, we must allocate space for our thread handles as such. So thread handles equals malloc thread times size of pthread t. That's gonna allocate space for 10 thread handles, and we pass in that thread handle into pthread create. The second argument after that, just pass in null for that. Don't worry about it for now. Start routine, we are passing in a function that our thread is going to run. So we're passing in an entire function for our thread to run, but we're also going to be passing in arguments. So the third and fourth arguments for pthread create. The third one is the function to be run. The fourth one is function arguments to be passed into the function. They are both passed in as data type void star. This is a data type that void star is a data type that can be passed to any pointer in C. For the fourth argument, this allows us to pass in multiple values into the thread function as a list of values. Also, the return type of our thread function, notice that was of type. The return type was void star. That allows us to get stuff returned from the hello function here. Though here we're not returning anything, so kind of doesn't matter here for this example. Anyway. The return type of void star allows us to have the function return multiple values. So, once we've created all of our threads, the main thread says hello world from the main thread. Once that's done, we call pthread for, and then we pass in each thread handle one by one. So we have to call pthread one by one. As we do, we pass in one of those thread handles. We do this in a for loop. So we use pthread join. So every call to pthread create must have an accompanying pthread join somewhere after that. When we call pthread join, we pass in a thread handle for the first argument and another variable called return value p for receiving any return values from the thread. We don't have anything for that, we're just gonna pass in null for our purposes. So the act of a main thread creating multiple threads and then waiting for them to finish, that's described by what's called the fort and join model. We call pthread join to free up any resources associated with that thread. If we fail to do so, we might get zombie threads, which might prevent the creation of new threads if left unchecked. If the main function doesn't need to wait for a thread to finish, we instead call pthread detach. But either way, whether it be pthread join or pthread detach, this frees up a thread's resources upon termination. That way we don't get zombie threads. That way we don't have like resources that cannot be deallocated and then reused for new threads. Also worth mentioning is the fact that every pthread function returns an error code. For the practice of writing good code, it's a good idea to use these error codes to check whether your code is working, and even more so for debugging. For now, we're just gonna ignore the error codes. So, section 4.4 is all about critical sections, and from there we're gonna get into our first program beyond just the pthread hello world pthread program. We're gonna write a program here, and then hopefully we're going to have a chance to. We're gonna write this program step by step and debug any and all issues that we encounter along the way. So really all of this is a preview for what we're gonna do next. And of course this is gonna be continued in the second slideshow. So part 1 of part A for chapter 4. Okay? So, as I said, this video is just gonna be the Hello World program that we're gonna be writing out. Okay? Next video is gonna be the real meat and potatoes. We're gonna write a multi-threaded program that's going to calculate the value of pi by adding hundreds, maybe thousands of fractions together. We're gonna do it single-threaded, and then we're gonna do it multi-threaded, and then we're gonna find issues along the way and hopefully solve all of them. Okay? Alright, so that's gonna be the end of the video, and see you next video. Alright, bye.